Okay, we're going to, although I did post sort of a last part of the chapter 12 about molecular polarity, I did want to just kind of cover a little bit here today. It is going to be on the exam on Wednesday, which again, we'll cover chapters 4, 11, and 12. No 5, obviously, on it, as my announcement, I think, came out and said. So we talked about drawing Lewis structures and all that, and we kind of left with molecular polarity. And like I said, there's another sort of lecture up there about it, but I did want to kind of cover it in person a little bit. So when we talk about molecular polarity, it is in a lot of cases different than what we talked about earlier, which is bond polarity. And bond polarity is really where we use a sort of difference in electronegativity values to determine whether or not a bond is polar or nonpolar. And again, remember, kind of like 0.4 and less is nonpolar. Anything above 0.4 is considered polar. Um, Molecular polarity takes into account the entire molecule as a whole, and whether or not as a whole it is going to be polar or nonpolar. Is it going to have equal sharing of electrons overall? Now, if it does have unequal sharing of electrons, and it will have a dipole moment, which is represented with that arrow that we saw when we did bond dipoles. The arrow points to the side that is more negative, and the back part that makes like a positive goes to the positive side. And polar molecules will possess this dipole moment. Nonpolar molecules will not. So nonpolar molecules are considered overall sort of equal sharing of electrons, kind of like a neutral molecule in a sense. There's perfectly kind of distribution of electrons overall. Polar molecules will have a positive side and a negative side. Now, the one place where kind of molecular polarity and bond polarity are really the same thing is when you're dealing with a diatomic molecule. And a diatomic molecule, as we talked about, basically, obviously, is basically two things bonded together. And in this case, the molecular polarity and the bond polarity will be the same. So if you have a homonuclear diatomic molecule, they're basically two of the same elements together, or atoms of the same element. So if you have something like H2, when we look at something like H2, that bond is going to be a difference of electronegativity of 0, obviously. They both have the same electronegativity values. That's going to make this bond a nonpolar bond. And because this is absolutely the only bond that's present in this molecule will also be a nonpolar molecule. So if I have something like oxygen, the difference in electronegativity here is going to be 0. That means that this has a nonpolar bond. And once again, because it is the only bond present, it will also make that molecule a nonpolar molecule. Now, if you have two different things bonded together, like HF, for example, what we know about the difference in electronegativity when you do this, it's about 1.9. And that would make that this is a polar bond. And in this particular case, because that is the only bond that's present, it would also make this a polar molecule. And it would have a dipole moment that can be represented by drawing that arrow pointing towards the fluorine, in this case being more electronegative. So the simplest ones to determine whether or not the molecule itself is polar overall is a diatomic molecule, because there's only one bond, and whatever that bond is in terms of difference in electronegativity, it's a polar bond or a nonpolar bond, that will be what the actual molecule is as well, because it's the only bond present. Question on that there. So diatomic, super simple, one bond, determine what it is, and that will also tell you what the molecule is, polar or nonpolar. If everything that was that simple, that would be great, but it's not. When you get to 3 or more atoms that are involved, you actually do have to look at two different things to determine whether or not a molecule is polar or nonpolar. And when you look at something where you have 3 or more atoms, you have to look at, again, are there polar bonds? And you also have to look at the molecular geometry. That's the shape that we talked about. So the classic example is if we look at carbon dioxide and we draw the Lewis structure for this, the bond between carbon and oxygen, they are in the same period on the periodic table. That would make it a polar bond where the arrows would be heading towards the more electronegative oxygen in that bond. So this guy definitely has polar bonds. So you may be inclined to think that this molecule is going to be a polar molecule because, it does have polar bonds, so it kind of makes sense. The second thing we have to look at is what is the geometry of this? And this guy has 2 electron pairs, 1 and 2, and also has 2 bonds, also 1 and 2. And that would mean that the geometry here is actually linear, and this is the molecular geometry we're talking about. It's basically a straight line, which means that if my pen was the CO2 molecule, I have oxygen pulling to the right. I also have oxygen pulling to the left, and I'm actually pulling really hard on both sides of my pen, and my pen is going nowhere. Yeah, so what they actually end up doing because of the geometry of this molecule is they actually will cancel each other out. And those guys will actually cancel out each other. And although this guy does have polar bonds, CO2 would be a nonpolar molecule because of the geometry of it. Now, if you take something like water, water also has polar bonds heading towards the oxygen in this case. And what happens in this case is because it has polar bonds, its geometry is 4 electron pairs around the oxygen and 2 bonds. That is bent or V-shaped. So what happens in this situation is you can kind of think of it, you got kind of like a molecule like this where it's kind of bent or V-shaped. You got electron density coming towards the top on both sides, almost like a string on top of it. If you just kind of pull the string from the top, you can kind of imagine the whole molecule will move. And they actually will add to each other in this case. And you'll get what is referred to as a net dipole moment happening in this direction. And this would be a polar molecule, where the oxygen side of water is more negative, the hydrogen side is more positive because of the unequal sharing of electrons that are happening in this case. This occurs because those bond dipoles, which are these guys, they are vectors. They have direction, they have magnitude. And I think in physics, that means in some cases they will actually add to each other. And in other cases, they will actually cancel each other out. So if you kind of did like the little head to tail type of thing, those two vectors in water would go something like this and then add to each other in that direction. And that's how we get the net dipole moment. Clearly, nobody wants to draw vectors or anything like that. So there must be a quicker way to do that. And there is. So there are certain geometries which are considered symmetrical geometries, and there are certain geometries which are considered unsymmetrical geometries. And when we talk about symmetrical geometries, and we're talking about the molecular geometry here. So for you guys, that would be trigonal planar and tetrahedral. And what these geometries have in common is if you draw the Lewis structure, there's no dots on the central atom. And what ends up happening is if you have no dots on the central atom and all the outside atoms are the same element, it will lead you to a nonpolar molecule. And that's because they're going to be perfectly equal and opposites of each other. So they'll either pull equal and opposite, or they'll push equal and opposites of each other, and they will essentially cancel each other out. So if you took something like this, and again, I'm not going to draw all the dots on the fluorine here, but there are dots. But if we look at the central atom, there are no dots. All the outside atoms are the same. This is going to be a nonpolar molecule. Even though, again, it does have polar bonds heading towards the fluorine in each of these cases, does have polar bonds. But again, you could think of it like a tug-of-war rope. Basically, everybody's going to pull on that rope equal and opposite of each other. So again, if everybody pulls on a rope equal and opposite to each other, the rope's going to go nowhere. They're just going to kind of cancel each other out. And that's what's going to happen here. So again, it demonstrates the idea that you can have polar bonds, but the molecule itself may be nonpolar because of its geometry. Now, what would happen if I took the same guy and I got rid of a fluorine but replaced it with a hydrogen? In this particular case, we would have these guys pulling this way, and the carbon-hydrogen bond is nonpolar, which means nobody's pulling that way. In this case, you would then have like 3 people pulling the rope this way, not very many people going that way, and they're going to beat that guy pretty easily and get him to move. And this will now become a polar molecule. So if you have a symmetrical geometry where you have no dots on the central atom, everybody on the outside is the same element, it's going to be a nonpolar molecule. Pretty safe bet. If you have no dots on the central atom, everybody on the outside is not the same element, it's probably going to be a pretty safe bet. It's going to be a polar molecule because you're going to get some type of unequal kind of pulling or pushing that's going to occur. Any questions on that there? That leaves us some unsymmetrical geometries. And unsymmetrical geometries for yourself there would be then trigonal pyramid, bent are V-shaped, and are angular, I think, for you guys is what you guys got. What these all have in common is if you draw the Lewis structure, you got some dots on the central atom. So you're going to have dots on the central atom. And if you have dots on the central atom and all the outside atoms are the same element, it is going to be a polar molecule. So for example, water like we just did, I see dots, I see same elements on the outside, going to be polar. We did SO2 the other day too. We drew something like this. I see dots on the central atom, everybody on the outside is the same. It's going to be a polar molecule. I see NH3. See dots, everybody's the same, gonna be a polar molecule. That is almost as quick as you can do molecular polarity. Dots or no dots, is everything on the outside the same or not the same? And you basically will probably be right 99.9% of the time without having to worry about vectors or anything like that. This also only leaves you linear geometry, which is pretty straightforward. Like the CO2 example, if they're pulling in opposite directions, they'll cancel. If they're actually heading towards each other as well, they will cancel as well. So it is possible, you know, if you have some type of thing that is, they're all pushing in on each other, they will cancel as well. It's like 2 people on opposite sides of a door that swings open. They both push equally. The door's never going to open, right? It's going to kind of be stuck there. They're going to cancel each other out. So if something kind of pulls or pushes in equal opposite directions, they will cancel. And obviously, you'll get a nonpolar. It is also possible that you could have a linear situation where everybody is actually heading in the same direction. In this case, it would then become a polar molecule because everybody's basically pulling one way versus the other. So linear is pretty easy, straightforward. And then basically you could go dots or no dots and probably pretty quickly get the right answer in terms of molecular polarity or if it's non-polar or polar. Any questions on that there? Okay, so I just want to kind of cover it in person with you as well. And again, I posted like a little snippet lecture on this as well up online if you want to watch it. So make sure you do if you haven't done so already. All right, then we're going to go off to chapter 5. So as we talked about last time, chapter 5 has been moved from the exam, and we'll do some type of quiz on it probably after spring break, I think. But we're going to talk about nomenclature. And nomenclature is naming, and we're going to talk about really the naming the two types of compounds that we talked about in bonding. So that is, again, your ionic compounds, which is always a metal and a nonmetal. And as we talked about there, that is going to cause a transfer of electrons, causing the metal to make a positively charged cation and the nonmetal to make a negatively charged anion. And again, as we talked about with bonding, there's no sharing of electrons happening here, right? The other type of naming we're going to talk about is really covalent bonding, or molecular compounds are sometimes referred to. These are two nonmetals. And as we talked about in bonding, we have some aspect of sharing going on, either equal sharing or unequal sharing happening. But again, there's some type of aspect of sharing. Depending on whether it is an ionic compound versus a covalently bonded compound, does make a difference in terms of how you go about naming. And that's probably one of the first things that you want to be able to do is identify what type of compound you're dealing with. Is it ionic? Is it covalent? Then that will also direct you sort of into the right way to name them as well. Now, there are certain things that we always go by sort of the common name. H2O is water. It is not a trick question. Answer water and move on with your life, yes, and get the point. Don't put anything weird. Nobody wants a refreshing glass of dihydrogen monoxide or anything like that, right? So it is just water. NH3 is ammonia. And CH4 is the simplest organic molecule you could have, which is known as methane. That stuff comes out when you light your Bunsen burner and spark it, and then it catches on fire. So those three you definitely should roll with always the common name here: water, ammonia, and methane. Also, as we get into naming, just a reminder, when we talk about things on the periodic table, they typically do not have charges when they are by themselves, right? So if they're not combined with anybody else, no element on the periodic table really has a charge. It only really gets a charge when we make an ionic compound, when the metal and the nonmetal basically come together based on those periodic trends where the metal wants to get rid of its electrons, nonmetals wants to pick them up, so we get that transfer of electrons that occurs. But when things on the periodic table do make charges, everybody in group 1 will make a +1 charge. Everybody in group 2 will make a +2 charge. When we get to group 3, I would say for the most part it's aluminum we're talking about here. We got kind of that staircase coming down. It will be +3. And then we have, gotta go that way. We have group 4. Actually, shouldn't have wrote that there when we read it above. Go that way with it. We'll go +3 that way. 4, 5, 6, 7, and 8 coming this way. We really don't have a great pattern in group 4 because above it's nonmetals, semi-metals, and metals on the bottom of it. We then skip and go group 5, and that is the nonmetals above the staircase we're talking about, -3. Group 6, -2, nonmetals above. Group 7, -1. So we go +1, +2, +3, skip, go backwards, -3, -2, -1 as we go there. Transition metals, which are here, they typically will make a variable charge, and that is because they have all those electrons, right? They got the s electrons to use, they got the d electrons available to them, so they can make multiple types of charges. Representative metals will only make one type of charge because they have only a certain number of valence electrons available to them before they get into their core electrons. And because of that, they will only form like a +1 charge. Like sodium will only form a +1 charge because as soon as you lose that first valence electron, you're now into those core electrons. As we talked about with the ionization energy is super high, it's not going to rip out any of those electrons, so that we will never lose it. And that's different than in your transition metals that have those S's. They also have those D electrons. They're never going to lose them all. And they can make a variety of sort of charges that occur because of that. They have all those electrons. There is 3 exceptions, though, and that is zinc and cadmium. They are transition metals, and these guys will typically make a +2 charge. If you hang a left at cadmium, you'll find silver, and silver will make a +1 charge. So those are fixed charges for those 3 transition metals. All the other transition metals within this area and also down in here below the staircase where we have like lead and like tin happening, those guys as well have the ability to make a variable type of positive charge. So in some cases, they may make like a +2, +3 charges, +4, +2. So they have a variety of charges that they can make. But everybody, again, in group 1, group 2, aluminum there in group 3, 5, 6, and 7, zinc, cadmium, silver will all have really kind of fixed charges no matter what the situation is. So when we name these binary compounds, which are basically just 2 atoms together, again, we're going to have ones that are metals and nonmetals, which is going to be our ionic compounds, and our 2 nonmetals, which will be our covalently bonded compounds. And as I mentioned before, there are different ways that we name each of these depending on the situation that we find ourselves in. And we do always, when we are dealing with ionic compounds, and that's a type 1 and type 2, and that is basically an ionic compound, which is obviously a metal and a nonmetal together. It is always the cation that comes first, followed by the anion. So both in formula and in name, it is always the positive guy first, followed by the negative guy. So when you name something, that is the way you should name it. Positive guy first, negative guy second. And when you're writing the formula, it should always be the positive one first, followed by the negative. We also talked about, I think, in an earlier chapter there in like chapter 4-ish, that when we put together 2 ions to make the formula for an ionic compound, it should always equal 0. And if you remember, the reason why when we put a positive ion and a negative ion together to equal 0, it has to do with the bonding that we were talking about the other day. That will allow everybody to get to that noble gas configuration in terms of electrons. So it allows everybody to get to that noble gas configuration. So we always want to put a positive ion and a negative ion together in the simplest way possible to do so. So that is why, again, when we take something like Na plus and Cl minus, that is +1 and -1, which means when we write the formula for this guy, we just need one of each. Remember that the formula does not have a charge. It needs to equal 0, again, in the simplest way possible to achieve that. But it is still made up of a cation, in this case, which is sodium, and a chloride anion, in this case. So ionic compound formulas do not have charges, but they are made up of things that are charged, guys, and ions. Also why when we took like our calcium when we were doing bonding and we put our F minus together, we realized that calcium was not happy giving away 1 electron, and the fluorine could only hold 1 electron. So we actually needed 2 of those guys, right? 1 for each of those electrons. And that gives us our proper formula of CaF2. That's going to get all 3 of these guys into that noble gas configuration and be really, really stable. So again, that is the purpose of putting an ionic compound together in the simplest way possible to get it to 0. By the way, if you were asked to write the formula for the cation for this guy, it would be Ca with a +2. And if you were asked to write the formula for the anion, it would actually just be F minus. not F2 minus, no such thing. Yes, so the 2 means that I don't have one of those. It means I have 2 of those. But if you're asked to write the formula for the anion, it should just be F minus. And if you're asked to write the formula for a cation or anion or any anion, it does need to have the charge written with it. So if you're just writing the formula for the charged ion by itself, not put together, just individually, either the positive ion or the negative ion, the formula does need to have the charge, and you should just write it for one of those guys by themselves. Any questions on that there? So how do we go about naming some of these guys? Well, when we talk about ionic compounds and we talk about type 1 and type 2 compounds, it is actually when we have a metal and a non-metal together, it is always, when you're naming anything, if you have a metal involved, that is really the most important thing to look at. So if you're trying to name something and you see a metal involved, that is really where you should look to try to determine how you should name this particular compound. The non-metal is not really that important in this case. It is really always the metal when it's involved. You should always do that. So when we look at type 1 versus type 2 metals, the difference between type 1 and type 2 metals is the type of charge that those metals can make. A type 1 compound is a metal that is basically from group 1, 2, 3. It's zinc, cadmium, or silver. What all those have in common is they all have a fixed positive charge. So as soon as you see the metal that's involved is from one of those locations, group 1, group 2, group 3, it is silver, zinc, or cadmium, it is a type 1 compound. And as we'll talk about shortly, you pretty much, that's all you need to know. Basically, that's the only thing you really need to figure out in that particular case. You could actually get right to the naming part after you identify that. A type 2 compound is one where the metal is a transition metal, or just to the right of it, where we were talking about where you find lead and tin underneath the staircase, basically. And what those guys have in common is, as I mentioned a second ago, they can have a variable positive charge. And in those cases, we have to actually do one extra step when we go to name them because they can make different types of charges. So for example, as you can see up there, chromium could be a +2 charge. It also could be a +3 charge. In certain cases, copper could be a +1 charge or a +2 charge. So because they have that ability to make multiple types of charges, it actually is important who they are attached to in terms of what charge you see. And again, as I mentioned a second ago, it's because really these transition metals have those s electrons and those d electrons. So they tend to have the ability to make a variable type of charge that is different, again, as I mentioned, than group 1 or group 2 or group 3, because those guys basically have a certain number of valence electrons, which as soon as they go through them, they're into the core electrons and they're not going to make anything else. So as I mentioned, sodium, no matter whatever you want to attach it to, every sodium ion will always be +1, no matter the situation. It will never change. But something like chromium in certain cases could be +2, it could be +3, it could also be like a +4 in some cases. It does depend on who the chromium is attached to as to what charge it's dealing with. So when we have ions by itself, the way that we go about naming these guys are, if they are a positive ion, a cation, we simply just use the whole name of the element. So H plus would be the hydrogen ion, Li plus would be the lithium ion, sodium Na plus, sodium ion, calcium, the calcium ion, and so forth, all the way down there. So if it is a positive ion, you pretty much just roll with the whole element name. It does nothing really changes. And if it's just the ion by itself, like you can see here, we have the formula, the symbol and the charge written, the symbol and the charge. And again, we just use the whole name. Now, nonmetals are a little bit different, and the anions are a little bit different. The anions, we typically take the front part of the nonmetal name and we leave it. We drop the last part of the name and we put IDE at the end of it. So we kind of get rid of the last part of the name and we drop in IDE. So H minus becomes the hydride, IDE. F minus goes from fluorine to fluoride, chlorine to chloride, oxygen to oxide, and so forth. So we drop sometimes a little bit more than the last part of the name, but it does end in IDE. You will also maybe notice that hydrogen there is interesting. It is the only element that could actually go both ways. It could be positive or it can be negative. I would say probably 99% of the time hydrogen is going to be positive, but it can be negative if it comes after a metal. So for example, if you had LiH, that is lithium, which is a group 1 metal, +1, and hydrogen in this case would actually be the negative version of hydrogen, and this would be lithium hydride. It would be the name of this. Once again, +1, -1 equals 0 in that case. So I would say most of the time hydrogen is going to be positive, but it definitely can be negative if it comes after a metal. Question on that there. So let's talk about type 1 and naming them. So as I mentioned before, type 1 is an ionic compound. It has that fixed positive charge. And as I mentioned before, as soon as you're able to identify the metal as a type 1 compound, you basically should just roll right into the name of it. And to do that, you're just going to use the whole name of the metal. And the non-metal name is going to get the IDE treatment at the end of it. There is absolutely, in the case like here, when we have a metal and a non-metal, when you see the metal, as I mentioned, which is the most important one there, you should never, ever, ever use prefixes in this situation. So people always want to use prefixes when they start naming these things because, you know, it sounds more chemistry-like, I suppose. But the way you want to remember it so you don't get a big X on your paper is if there's a metal involved, don't lay up a prefix. Yeah, that's probably wrong. So should never, ever use a prefix if there is a metal involved when you're naming these things. That means pretty much for all ionic compounds, never, ever use a prefix pretty much when you have a metal and a non-metal involved. So really, metal, no prefix. There is a time and place for prefixes, and we'll talk about it shortly, but this is definitely not the time or the place to do that. So here we have NaCl, which is, again, our sodium chloride. We want to identify what we're dealing with. So that is a metal. That is a non-metal. So as soon as you see that, it should trigger to you that this is an ionic compound. And what you should think about then is, as I mentioned, it is the metal that is the most important thing to look at. You want to go to the periodic table. You want to find sodium. Should be hanging out there in group 1. Because it's in group 1, that should signal to you it is a type 1 metal. And as soon as you do that, all you have to do is whole name of the sodium here. And our chlorine becomes chloride, IDE at the end of it, and we put it together. Same thing down here, Ki. That is a metal and a non-metal, right? And same deal, that should signal to you it's ionic. Looking at the metal, which is the important thing, that is potassium, which is also in group 1. That has a fixed positive charge. That should tell you it's a type 1 compound. And as you can see down there, you could go with potassium iodide, IDE at the end of it. This again is a cation that is +1 and an anion formula of -1, which again is why when we put it together, we just need one of each of them to get to 0. So if we looked at something like our CaBr2, again, we want to look at it. That is a metal. That is a non-metal. And that tells me it's ionic. Looking at calcium, that is group number 2, which has a fixed positive charge. Tells me it's type 1. We're going to roll with calcium bromide. And this is what I was talking about earlier. People see this and automatically they start yelling dibromide here, yes. So you do not use a prefix here. It doesn't matter if you got 400 of the Brs, 300 of the sodiums or calciums. You just use the name of it basically appropriately. No prefixes involved. Obviously, the 2 is because calcium has a +2 charge. Each of the Brs are -1. And we need not 1, but 2 of them to balance out the +2 charge that's happening in this case. Once again, if you were asked to write the cation for this, this is what you should write with the +2. If you're asked to write the anion, that right there is what you should write for the anion. Again, no Br2 on the bottom, minus on top, does not exist. So again, just the ion by itself with the charge if you're asked to write it. Again, you can see in all these formulas, we have a formula that has no charge, but in reality, they're all made up of stuff that does have charges. And if you had this in a solution, you would have calcium ions floating around and bromide ions basically floating around in the solution, having a good time and moving around. Question on that there. All right, so why don't you give these a try, and I'll give you some names here. Why don't we do... Let's do a little sodium oxide. Let's do magnesium nitride. Let's get rid of this one since we already did that one. Let's do, we got there, KZ. Now let's do AgCl. Let's do, cadmium bromide. And I don't know, let's do aluminum sulfide. All right, let's do names on the left and proper formulas on the right. Okay, let's take a look, see how you're doing here. So we'll start here on the left. Again, really the first thing you should probably do is identify what you're dealing with. So potassium is a metal, Cl is a nonmetal. So that should tell you it's ionic because you do have a metal and a nonmetal. Once again, as we talked about, when a metal is involved, that is really where you should go. And when you see potassium, that is group number 1, which tells you it has a fixed positive charge. So that is a type 1. That, frankly, as I mentioned, all you need to do for this, and you can now name it. You're going to use, again, the whole name there of our metal, which is potassium. The chlorine gets the IDE treatment at the end, and that would be potassium chloride. The cation in this case is K with a +1 charge. The anion is Cl minus, -1, +1. You just need one of each of them to put them together in this particular case. Any questions on that one there? Next is zinc, which is a metal. S, which is a non-metal. So that tells you, once again, it's ionic. We look at the zinc. It is not a group 1, group 2, or group 3, but it is one of those transition metals that does have a fixed charge, one of the 3 exceptions. So because of that, that tells you it's a type 1, and you could just go to naming, which is zinc sulfide in this case, IDE for the second guy. The cation here is zinc with a +2 charge, sulfide with a -2 charge. So again, +1, +2, and -2 gives you 0. One of each of them are needed. Here we went to silver, which is a metal, chlorine, which is a nonmetal, again ionic. Silver, also one of those three transition metals that have a fixed positive charge, tells us it's type 1. At that point, that's all you need to name it, silver, and again, IDE for the end there, a little silver chloride in this particular case. Our cation, again, being our silver ion, and our anion being our chloride ion in this case. Lastly, that is barium, which is a metal. We got hydrogen, which is a nonmetal, telling you it's ionic. Barium group number 2, fixed +2 charge, tells you it's a type 1. And then you're ready to go into naming barium. And that is the negative version there of hydrogen. So that would be hydride. Again, the cation is Ba2+. The anion in this case, H-, not H2-, but just H-. The 2 again here means you have 2 of them. Yeah, so again, that is the formula for the anion. That is the formula for the cation. Any questions on any of the names here? Yeah. Now, when we have the name and we want the formula, we also want to kind of think about what we got going on. Sodium is a metal, oxide is oxygen is a nonmetal. Again, tells you it's ionic. And once you know it's ionic, what you want to do is just find the 2 basic ions that make up each of those things. So sodium is group number 1, which means it does have a +1 charge. Oxide is oxygen group number 6, which means it has a -2 charge. Once again, we want to put these together to equal 0. And in this case, you should hopefully be able to see you actually need one more of those. That's going to give you a +1, +2 to balance out the -2. By the way, if you draw it like that, you can just count what you just did there, 1 and 2. So that's 2 sodiums and 1 oxygen. So it should look something like that in that particular case. Question on that there. Now, sometimes people are taught to do the crossover move with the charges and the subscripts. And again, you could do that. It will work, like 93% of the time. If you're good with that, then you could just do that blindly and just kind of swap them over. But it will not work 100% of the time. So you will get some wrong if you do that. So sometimes it's better to think about balancing out the charge rather than doing that. And again, if it helps you just to draw it, it sometimes is also really helpful. Magnesium, which is group number 2, is +2. Nitride is nitrogen group 5, has a -3 charge. The common number between those two is 6. If you're not sure, you could just multiply those together. 3 times 2 is 6. So to get my magnesium to 6, I need 1, 2, and 3 of them. That gives me a +6 overall. Over here, I need 2 of them, gives me a -6. And again, to get the proper formula at this point, you can just count 1, 2, and 3 of those. So 3 magnesiums and 1 and 2 of those. 2 nitrogens will give me my answer in that case. And again, sometimes that's helpful to kind of see it that way. Cadmium is a transition metal that has a fixed charge of +2. Bromide is group 7, which is a -1 charge, metal, non-metal happening here. Again, when we put this together, we do need one more of the Br minuses. That gives me a -2 on the right to balance out the +2 on the left. And again, if we just count what we got going on there, CD, and we got 2 of those. So Br2 in that case there. Any questions on that one there? Lastly, we have aluminum, which is +3, and sulfide, which is group 6, -2. Once again, we're going to hit a 6 as a common number. And again, to get the aluminum to 6, I just need 2. To get the sulfide to 6, I need 3 of them. If I count it up, that is 2 aluminums and 1, 2, 3 of those sulfurs. And I could put them together properly here and get our formula. Any questions on any of those names or formulas in this case here. So again, if it helps you to do so, I would, draw it out like that. So you could, sometimes it helps visually to see what you got going on so you can kind of get the right formula. You do not have to obviously do that or anything like that to show the work, but if it helps you do so, go for it. Obviously, if you're asked these questions, these are the sort of answers we would be looking for and the total formulas here. But if it helps you to do the other stuff, kind of draw it out to visualize it, go for it. That way, at least you'll get the right answer, right? So any questions on that there? Question on type 1 compounds. Okay. Then let's talk about the next type of compound, which should be our type 2 compounds. So type 2 compounds are also ionic compounds. They also are a metal and a non-metal together. And once again, as I mentioned, it's always that metal that's the most important. And in this case, it's going to be a transition metal, or just to the right. And what we were talking about with these guys is they can have a variable positive charge. So we actually name these guys the same way as we do group 1 or type 1. The difference is because they can have a variable charge, we kind of have to tell people what charge we're dealing with. And to do that, we will basically use the whole name of the metal. We will also still do the non-metal that gets the IDE treatment. The additional thing that we do in the middle is we put a Roman numeral. And the Roman numeral is the actual positive charge on the metal. It is if you took out one of the positively charged ions out, what the actual plus charge is, an actual number is what the Roman numeral is. Very commonly messed up on by people is they think the Roman numeral means how many metals they have, and that is not the case. It is actually, again, if you took out one of those positively charged metals, what the actual positive charge is on it, and that's what you should use for the Roman numeral. So for example, here we have FeCl2. So again, we'll go through our same sort of system. That is a metal. That is a non-metal. So once again, that should, as we talked about, check off the ionic box. We look at the metal, which is iron. It is dead center in the transition metal region, which should definitely tick off the box there that it is a type 2, and it can have a variable type of charge. And I will need to use a Roman numeral is pretty much what it should tell you. So the good news on these guys is you will always 100% of the time know what the charge is on whatever it's attached to. So for example, here I got myself an iron that I'm not maybe sure what the charge is, but I do know the charge on my Cl, and Cl is group number 7, which means it has a -1 charge. There's not just one Cl in this case, but there are 2, and that's going to give me a grand total of -2 in this case. To balance this out to 0, that means the iron here must be rolling with a +2 charge in this case to get us to 0. That means at that point, once you figured out the charge on the metal, you basically could roll into the naming. We're going to go with iron, Roman numeral 2. Again, that is for the charge on the individual metal. And even though we have multiple Cl's here, just like in type 1, does not make a difference, no prefix. And this is going to be iron Roman numeral 2 chloride. Again, the way you should remember the no prefix, got myself a metal here, right? So not going to use a prefix. So that, again, is a good way to remember it. Should not be doing that. The reason we need the Roman numeral in this case is if I had FeCl3, we got kind of the same situation. That's a metal. That's a non-metal. That is still our transition metal. So in this case, we have an iron, but we have in this case 1 Cl, 2 Cls, and 3 Cls. that gives you a -3 charge. In this case, to balance it out, the iron actually will have a +3 charge. And the name on this guy would be iron Roman numeral 3 and chloride. And that is, again, where the Roman numeral 3 comes from. So the reason we have to use the Roman numerals for this type of naming, type 2, is because the metal has that ability to make a variable type of charge. And frankly, we need to tell people, hey, in this case, we're talking about the iron with a +2 charge. In the other case, we're talking about the iron with a +3 charge. The reason we do not, again, need to use Roman numerals with type 1 metals is there is no possible way ever that sodium will make anything other than a +1 charge. So it's like common knowledge of it's always going to be +1. So you don't need to tell people, hey, that guy has a +1 charge, because it can't be anything else. But in the case of iron, it can be something else. So you have to tell people kind of, in this case, we're talking about the guy with the +2, or in the next case, we're talking about the guy with the +3. Any questions on that there? Pb is a metal, oxygen is a nonmetal, so once again, that should tell you it's ionic. We look at lead, it is not a transition metal, but it is one of those ones that are below the staircase to the right that does have a variable charge. So it is a type 2 metal. And again, any of those metals where lead is, tin, antimony, bismuth, in that area, they can have also a variable type of charge. So we want to do the same thing. We have a lead. We do have oxygen, which is group 6, has a -2 charge. We have not one of those, but we actually have 2 of them. That together is a -4 charge. That means the lead here is +4 in this situation, not +2, by the way. So that would give us lead Roman numeral 4 for the charge and oxide. This is a prime example of what I was talking about earlier, that sometimes people are taught like this, just move it this way, and you will get the wrong answer in this case again. So there are a lot of cases where if you just blindly kind of move those things up or down, you will get the wrong answer in this case, yeah. Well, technically speaking, transition metals can go crazy, but they typically won't. I would say in most cases, probably most common, 2, 3s, 4s is probably, where you're going to see it, but you can have upwards of 6, 8. It can technically be anything, to be honest with you. And for example, something like Mn there in the transition metal region could have something like, like 8 different oxidation states running from like +8 all the way down to like, +1. So it could have a variety of stuff. But I would say most commonly in the transition metal region, 2s, 3s, and 4s are probably the most common ones that you'll come across. Yeah. Yep. Other questions? All right. So when we look at this kind of type 2 naming, there is actually an older sort of method that's sometimes used where they do not use Roman numerals, but they kind of use an old school name for the metals. And they will either end in ic or ous. And the one that ends in ic is usually the larger positive charged ion. And the one that ends in ous is usually the smaller positively charged. Think of like I ate too much or too much there. I feel icky is a good way to remember that. The good news is we really will not use kind of this older way of naming for the most part. I mention it because still today, people do use this older way of naming, and it does pop up, especially for things like iron and copper. It's very common. You might hear cupric or cuprous for copper, or ferric or ferrous for iron, and they still are used a lot today. So I would say out of any of those, probably those two, copper and iron, sometimes people will use that. But for us, strictly here, we will roll with the Roman numerals. So we will not use that older way of naming. Here's a table, I think, that shows that. So you can see there, ferric, ferrous, cupric, cuprous. You see it also uses kind of the older school naming for some of the elements. So we will not really use that here, and probably in most chemistry classes that you take, you don't really use it. But it does in papers, and sometimes they do still, you kind of use it for copper and iron a lot. We will strictly roll with the Roman numerals in this type of situation. One of the type 2 metals that confuse people a lot is this guy right here, and that is mercury. And mercury can look like this, and mercury can look like this. And once again, the one with a lot of 2's is actually mercury 1. And the one with only 1 2 is actually mercury 2. And the reason for that is mercury 1 is actually not perfectly drawn, but 2 mercury 1s stuck together, basically. So that is why it has a +2 charge. +1 and +1 is +2. And that is why there is a 2 on the bottom to indicate that there's 2 mercuries there. So that's just how kind of mercury 1 comes. So oddly, the one with all the 2's is mercury 1. The one with the least number of 2's is actually mercury 2. How would you know in a formula if you're dealing with mercury 1 or mercury 2? The bottom 2 here tends to stick around. And what I mean by that is you could have something like this, and you could have something like this. And here, this is mercury 1 oxide. This is mercury 2 oxide. And the reason for that is, as you can see here, that 2 actually sticks around for mercury 1. So this guy here is Hg22 plus and O2 minus. This guy here, which is mercury 2, is Hg2 plus O2 minus. So the way you could kind of recognize if you're dealing with kind of the mercury 1 is that 2 does tend to stick around on the bottom there. And that is, again, how you could kind of identify it. Any questions on that there? All right. So as we talked about, the additional thing we're going to do is use a Roman numeral to indicate the charge on the metal. So why don't we try a few here? Guys on the left there, let's go names. Guys on the right, let's go form. Okay, so since we're getting to the end, let's take a look at it here and see how we're doing on them. First off, identification, cobalt metal, non-metal. So once again, that should send you to the ionic category. Always the metal importance, so cobalt pretty much center of the transition metal region should tell you it has a type 2, has a variable charge, means we should be Roman numeraling this guy at some point. We need to figure out the charge on it. So we got 1 cobalt. We definitely know that Cl is group number 7, and there's not 1, not 2, but 3 of them. That's going to give us a -3. Again, to balance it out there, the cobalt has to be +3 to do so. That's all we need to name it. Cobalt Roman numeral 3, once again, for the charge. And even though we have multiple chlorides there, it is just chloride at this point. Again, the anion would be this formula, and the cation would be that formula there. Any questions on that one there? Coming here, Cu is copper, metal. I is non-metal. Once again, that's ionic. Copper transition metal, type 2, multiple charge. Again, figuring it out. Copper, not sure the charge, but I do know I is group 7, should have a -1 charge. To balance that out, we just need a positive charge there for our copper. And that, again, is all we need. So that's going to be copper Roman numeral 1 for the charge. And iodide. Questions on that one there? Next is Sn, which is tin is a metal. Br is a non-metal. So once again, ionic. Tin, not a transition metal, but one of those below the staircase to the right that falls under the same category. So it can have a variable charge. Once again, I don't know what it is, but I know bromine is group 7, so that's a -1. And again, here I don't have just one of them, but I do have 4 of them. And that's going to give me a -4 charge to balance it out to 0. Plus 4 it would has to be. That's going to give me 10 Roman numeral 4 for that charge. And once again here, bromide. Any questions on any of those names there? Now, if I have the name like I do on the right and I want the formula, not a lot to figure out here because when it says iron 3, what's the charge on the iron? It is a 3 plus. It actually tells you, right? So you don't have to figure anything out. So that's kind of nice. Oxide is oxygen on the periodic table, which is group 6 minus 2. Common number between 3 and 2 is 6. So to get my oxygen to 6, I need 3 of them. And to get my iron to 6, I need 2. So again, if you just count, that's 2 irons. And that's 1, 2, 3 oxygens. Yeah. A little Fe2O3 action happening there. Question on that one. Next, nickel Roman numeral 4 means I have a nickel that has a +4 charge. Chloride is Cl minus. Once again, at this point, +4, we'll need to balance it out. So I need a grand total of 4 of those chlorides. Give me a -4, 1 nickel. I'll just come down here. 1 nickel and 1, 2, 3, 4 of those guys. Going to give us our proper formula in this case. Again, if it helps you to draw it out like I'm doing, do it. So at least all you have to do is count it at the end and you'll get the right answer. You don't have to do that, obviously, in this case. And lastly, tin Roman numeral 2 means my tin has a +2 charge. And phosphide is phosphorus on the periodic table. Again, common number, 3 times 2 is 6. I would need 2 of these guys. And my tin, I would need a few of those. And that's going to give me a +6 to balance out my -6. 1, 2, 3 tins. And 1, 2 of those guys. Yeah. Gives me my proper formula here. Any questions on names or formulas of type 2 guys? Yeah. All right, we're going to lay it up there. And before you